All right, so today's lecture will be basically us discussing what a system is. Right, so we'll look at what a system is, then classifications of systems, and then we will take a look at an overview of a communication system. Okay, so then we are done with the lecture notes. It's actually not too much, and I believe we can finish it today. So we have this page, but I will ask what you think a system is. For example, when you hear the word Ghana's education system, okay, what comes to mind? If somebody says that, oh, Ghana's education system is not as strong as maybe China's education system, what comes to mind when you hear the word system in this wise? Please, you can unmute yourself and then answer. I'm actually waiting for an answer. So can somebody give us an idea of how you understand the system, not based on what has been posted here?
Hello. Okay, madam. Please, what I understand about system is that it's a group of components that work together to achieve a specific purpose or task.
Okay. Yeah, thank you very much. That is a very, very excellent explanation of what a system is. So it means that a system has to achieve a certain task. There is some work for that system to do, and that system should be able to achieve that work. So which means that, for example, talking about Ghana's education system, there is a task that system is supposed to achieve. So you enter it when probably you are a baby. When you are done with it, let's say at the point of HND level or BTech level or PhD level, you should have a certain outcome, right? We should be able to see a certain outcome from you. Then we know we can measure the efficiency of the system in that way. And please give me just a moment. I'll be back. Okay, so I'm back. I'm sorry for the short absence. Okay, so like you said, the definition for system, like I said, is perfect, right? There has to be an input, and when we have that input, we are expecting the system to go through certain processes to give us an output, and we are going to check the efficiency of this system based on the output when we compare with the input. For example, if we take Ghana's education system and then we send a baby who has now learned how to say mama dada, and if after university time that child who is now, let's say, 26 years can only say mama dada, it means that the education system was not efficient in building certain processes or changes within that child, right? And so any system at all must first of all have an input, all right? And this input, sometimes you are referring to it as excitation. It should have something that it is going to work on, and it should have an output, right? The output compared with the input will give us an understanding of how efficient that system is. So we will refer to the output of the system as Y and the input as X, right? So T is a combination of all the processes that the system is going to do on X. So we expect that after X has had an encounter with the system, as in the T, we should get a certain output Y, right? So let's say we have a system that is supposed to multiply inputs by 5. So if we put in 5 loaves of bread, we expect that the system is going to multiply that 5 with 5 and give us 25 at the output, right? Then we know that the system is working well because the system's definition is 5x. So 5 is the process, is multiplying the inputs by 5 is the process the system is supposed to go through, right? So we have different types of systems. About 4 of them, 3 of them are written here, but there is a 4th, which we will discuss as we go through these 3. So we have the single input, single output system. So for this system, what we expect is that when we have put in one thing, we expect just to have one thing at the output. An example is let's say using Ohm's law, right? We have V is equal to IR. Now the resistor there is our system. The resistor has a certain resistance R. So when we apply when we have current flowing through that R, we expect to get an output, which is a voltage, right? So the voltage is just one output we are expecting from putting a current through a certain resistor with resistance R. Okay, so making this resistor a single input, single output system. Now we have multiple inputs, single output system. This means that for that system, we put in more than one input because it requires more than one input. Maybe a simple example would be a modulator. A modulator combines two input signals, right? So we have one input here, another there, and then it will combine these inputs and give us one single output, okay, which is the combination of the two. So for the inputs, we have I believe we have gone through this before, but we also have a revision of it. So the input is a certain baseband signal, okay, or original signal, and a carrier wave. These are inputs to this system, okay, and the system is supposed to produce a modulated wave at the output, right, making it a multiple input single output system. Another example of a multiple input single output system is a multiplexer. A multiplexer picks up different signals at different center frequencies. For example, let's say for television signals, right, we may have different television signals, right, coming from different channels, all of them put together into a certain device, okay, which we are calling the multiplexer. Then the multiplexer has a single output where it has combined all of these channels into one, giving it one huge channel bandwidth, okay, and then this one channel bandwidth is transmitted, right, and so everything is transmitted in one huge channel, but these are tiny or let me say should I call it semi, these are sub channels, right, put together on one huge channel and then transmitted outward, so that when the receiver receives it, that receiver will now be able to divide all the combination into sub channels, and these sub channels can be chosen, right, as you watch on TV or maybe on when you listen on radio or something like that. Okay, so these are multiple inputs. It has multiple inputs. However, the output is just one. Okay, then we have multiple inputs, multiple outputs. So it's just like this one, except that we have two outputs. Okay, one is maybe, well, from our example, let's say we receive a television signal, which is combination of the picture signals and then the audio signal. So that becomes the input. And then it's one, okay? Let me erase this. So both the picture signal and the so we have TV signal, which contains both the picture signal and the sound signal. Then our television system is going to separate these two, okay, so that it sends the picture to the screen and then it sends the sound to the sound system, right, so that we can hear what's probably if it's a newscaster, what the newscaster is saying, as well as see that newscaster. So it means that that system there, the TV system there, it becomes like a single input, multiple output system. Then we also, okay, here, sorry, I'm talking about a single input, multiple output system, but we also have a multiple input, multiple output system where we have more than one input and we also have more than one output at the end of the work of that system. Okay, so these are examples or the types of systems we have. And please, I don't know if anybody has a question. If you have a question, kindly unmute yourself, or maybe if you have a contribution on what we have talked about so far, you can unmute yourself and let us hear you.
Good evening, madam. My name is Moses Atembila. I want to inquire from you about the single input, multiple output. So that one, is it going to be X, and the output is going to be Y1 and YN.
Sorry, please come again with your question. Sorry.
Yeah, my question is, you just explained the single input and multiple output.
Yes.
So I want to find out whether the input is going to be X.
Yes, the input is still single, it's X.
Okay,
But it's going to have multiple outputs.
that's Y1 and YX.
Yes,
Sorry,
you have
YN.
Y1, Y2, Y3, etc. But the
Okay.
single is just a single input X.
Okay.
Yeah.
Thank you so much.
Thank you too. Okay. So the classification of systems, we have continuous time and discrete time systems, memory systems, and then memoryless systems. We have causal and non-causal, linear and non-linear, time invariant and time varying systems, linear, time invariant systems, feedback, and then stable systems. Now, the point of having these classifications The point of having these classifications is not to say that if, let's say, a system is continuous time, then it cannot it cannot have memory or it cannot be memoryless, right? But then to say that at any point in time, we may be able to classify all systems in these different ways. So we can classify all systems and call some as continuous time and some as discrete time systems. Okay, then we may also classify all those systems, the same systems we just classified, as systems that have memory and systems that don't have memory. So one system can be continuous time and also be a system that has memory. In the same vein, a system can be discrete time and be a system that also has memory or memoryless. Right. Then we can also classify all those systems into causal and non-causal systems. We can classify all those same systems that we have been classifying as linear or non-linear systems. Right. So I hope we get what I'm trying to say. All systems can be classified in terms of these. Okay, either causal or non-causal. Then those systems can also be classified as either linear or non-linear, right? We are not saying that once you classify a system as continuous time, you cannot also classify it as linear or non-linear. This, I hope we understand what I'm trying to say. All right, so then what is a continuous time system? We want to look at the various classifications. So when we classify a system as continuous time, it means that its input signals are continuous time signals and its outputs are also continuous time signals. Okay, so that will mean that for that system, we put in continuous time signals and we are expecting a continuous time signal at the output. Now, when we say a continuous time signal, we are talking about a signal that has a value at every point in time. At every point in time, you will be able to find a certain value for it, as opposed to discrete time signals. A discrete time signal is shown in figure 3 and continuous time signal in figure 2. We can see that for the discrete time signals, they are only defined as specific points in time. For example, assuming that n here is a time series, right? Then we are assuming that at a time t is equal to 0, there are certain times that came before it. Okay, so we have, let's say, -5, right? So at -5, we have defined that that signal is 0, but we don't have any definition for the signal at -4.8. Okay, in between this time, it is 0. And then it is now defined only at -4 as 0. So we don't really know its actual value at 3.8, 3.9, all the way to -3. Okay, and at -3, immediately that signal is around 1. As we see here, it's around 1. And then at -2 is around 2. But we don't know between -2 and -1, whatever was there was not recorded, right? So the difference between discrete time signals and continuous time signals is that continuous time signals always have a value. At every point in time that you pick, you will be able to get an amplitude for that signal. However, for discrete time signals, they are only defined for specific time periods or time points. You will not be able to find them defined at any other time except those specific time periods. Okay, and so systems that have discrete time inputs And then they also have discrete time outputs, signals. They are known as discrete time signals. And systems that deal only with continuous time signals are known as continuous time systems. I think I said signals for the discrete time. So what I mean is that systems that deal with discrete time signals are known as discrete time systems. And systems that deal with continuous time signals are known as continuous time systems, right? So it all depends on what is input to it and what the output is, right? And we should also note that within a certain process, let's say a certain system, there can be subsystems, okay? So systems that work with within, so for example, if you have a huge system that produces a discrete time output from a continuous time signal as its input, it means that it has various subsystems within it, and a certain subsystem will produce a certain output, and that output is then given to a subsystem within it, which may be a discrete time system within it, that will have a discrete time input and then give you a discrete time output. Okay, so different systems and the processes within them and how they eventually work to give us outputs. Then for systems with memory and systems without memory, we are dealing with systems that require previous inputs. If a system has memory, it remembers, or it has some information from previous processing. It has already processed something and it still has some of the outputs and sometimes some of the previous inputs in its memory, and therefore it falls on those inputs in along with the current inputs in order to give us an output. Okay, so an example of a system with memory, a simple example, is a capacitor, because capacitors store we know they store charges, and because they store charges, it means that they have some bits of the previous process still within the system, right? So whatever is input within it works with the previous information that the capacitor has already worked on and then stored. But when you take a resistor, for example, it only gives you the output for the current input. It doesn't store anything from the previous data or from previous processing. So once the voltage is taken off, there is no current kept, there is no charges still within it, right? And so a resistor is a simple example of a memoryless system, and a capacitor is a simple example of a system with memory. Please, if anybody has a question, you can lift up your hand or you can send it in the chat. I will see it and then I will address it as we go. Causal systems and non-causal systems. Causal systems are systems that only depend on previous data. So it's the output depends on previous inputs to make a decision. Okay, so always your output depends on the current inputs or the previous and current inputs only. Okay, but when you talk about the non-causal systems are systems that depend on current inputs and future inputs, and actually they are used to predict future events. However, since it is not very realizable, we can't easily create it and realize it because we don't know the future in current times. What usually happens is it is assumed, the future values are assumed based on previous trends, right? So those future values that are assumed can then be used as inputs for that system to predict future events. But causal systems, they are the ordinary systems we work with. Certainly systems that you are now inputting data in, or previous inputs that are already there that are now used to help that system to predict something or to give us a certain output. Okay, all systems that we usually work with are causal, right? Non-causal systems are not so easy to realize in actual real life activities, and therefore they may be in existence theoretically, right? However, they are not actually real because we don't know the future in order to put the future events as inputs. However, we may be able to assume future events based on the past trends and then use our assumed future events as inputs so that we may be able to help the system to give us a very strong predictive output. Okay, so which means that the opposite of causal is non-causal. Okay. Now, linear and non-linear systems. When we say a system is linear, that system is supposed to satisfy two conditions. The first one is that it's supposed to have what we call additivity. Okay. Additivity means that once we have defined the system, let's say as we have here, y1 is equal to tx1. So if we put x1, right, we are supposed to get, for that system, it's supposed to give us y1. When we put in x2, it's supposed to give us y2. What it means is that when we input a certain value x, we are supposed to get an output that is based on the x that we have input. And then if we input a certain value x2, we are supposed to get an output y2 because of the x2. Right? If we are getting those outputs and then we are able to find that they also add perfectly, as in we have tx1, okay, plus tx2 should give us y1 plus y2, and it actually works that way, so that the system then x1 plus x2 really give us y1 plus y2, then we have a system that it has the additivity property, right? It means that when you take individual outputs from certain individual inputs and then you sum those inputs, you put both inputs into the system, right, you will get the sum of, if you had just taken those individual outputs and then added, right? Let's look at an example. Let's say we have a system y is equal to, let's say 2x, okay? Now, if x1 is equal to 4, okay, x2 is equal to 7. When we put x1 as 4 in this system, we have y is equal to 2 times 4, and that should give us 8. Okay, that's y1. Now y2 is equal to 2 times 7, and 2 times 7 should give us what? 14. Okay, then if we combine x1 and x2, okay, so that we get x1 plus x2 is equal to 4 plus 7, and that gives us 11. Okay, then when we put that 11, which is x1 plus x2, into y, so then y is equal to 2 into brackets x1 plus x2. Will it give us y1 plus y2? If it gives us y1 plus y2, then it means that the system has additivity. So x1 plus x2 is 11, right? So let's put that in. So this is equal to 2 times 11, and 2 times 11 is equal to what? 22. Now let's look at y1 plus y2. y1 is what? 8, and y2 is 14. When we add them, we are also getting 22. So because we are getting these outputs, okay, y1 plus y2 being equal to 2 times x1 plus x2, it means that this system has additivity, and that system we are talking about is this. Let me use a different color. The color doesn't want to open. Okay, so the system we are talking about is this. This is the system, all right? And this system has additivity. Okay, so this has additivity. Okay, now another thing that a linear system, another characteristic of a linear system is that it is also homogenic, or it has homogeneity, or it can be scaled. When a system can be scaled, it means that if you give it a certain scalar value, if you multiply it by a certain scalar value, you should get a linear multiplication of the output. Okay, so for the system we have here, this example system we have here, which is y is equal to 2x. For this system, right, if we want to check to see if this system is scalable, or we can scale it, we just have to multiply this system by a certain scalar value. Let's say we multiply it by -5. Okay, so this is the scalar, right? But x is equal to 8. So now if x is equal to 8, y will be equal to what? 16. This implies that y will be equal to 2 times 8, which is 16. Okay, so if y is equal to 16 and we multiply this the input by -5, so we have 2 times 8 times -5, right? Are we also going to get an output of -5 times 16? And we see that we are certainly going to get that output. Okay, if we multiply 2 times 8 and then -5, we have what? -80. And when we multiply 16 by -5, we also have -80. So it means that this system, which is y is equal to 2x, is a system that has additivity. It also has homogeneity. And so it means that it is a linear system, right? Then it also means that any other system that doesn't obey either of these, or it only obeys one but it doesn't obey the other, is not linear. For a system to be linear, it has to follow these two conditions. So if it doesn't follow any of these conditions, or it only follows one of these conditions, then that system is not linear. Okay, so an example of a system that is not linear is what we have here: cos x and then y is equal to x squared. The reason why y is equal to x squared is not linear is because if you put in an x, that is, let's say x is 5, okay, and then you want to scale it, so you multiply it by -1, right? When you put in x as 5, x squared will be what? 25. But when you put in a minus and then it becomes -5 and then you square it, it will not be equal to when you square -5, you still have positive 25, right? So giving it a scalar value of multiplied by a scalar value of -5 does not make the y, when you multiply the y2 by -1, when you multiply the input by -1, it doesn't reflect the same as multiplying the output by -1. When the input is -5, when we square it, we have 25. And then when we multiply the output by -1, we have what? -25. So then it means that x squared is not linear. It's not linear because when you make scalable changes in the inputs, it does not reflect in the output. Okay, so the same for cos x. All right, cos x is also not a linear system. However, resistors and capacitors, they always give us linear outputs based on the inputs we put in. Okay, so a system is called time invariant if a change in time will not affect the output of the system. So if we shift or we delay the system, right, it doesn't, the effect is linear. It goes along with the delay. So we delay the inputs, the output is also delayed. We shift or we advance the inputs, the output is also advanced. Okay, and so when it's able to cause a similar shift in the output, we say that it is time invariant. It is time invariant. Now, if a system that acts differently from this is a time varying system. Okay, it's a time varying system, which means that it doesn't act linearly with time, right? It varies on its own with time. And a system that is linear, which means that it is able to satisfy the two conditions of linearity, and it is also time invariant, is known as a linear time invariant system. Well, feedback system is, as the name projects, a system that has parts of its output fed back to the inputs in order to help the system to be more stable, right? And examples of these are, I think, amplifiers. Some amplifiers they have their outputs fed back to the inputs in order to help the amplified outputs work more efficiently. Okay, so before we go to elements of a communication system, I am opening the floor for any questions anybody may have. Please unmute yourself if you have any question.
Madam, once again, Mrs. Atembila.
Okay.
Please, can you work an example of the formulas you are given that we can brace ourselves well with it before we move forward?
The formulas.
Yeah, the linear systems you get calculated, giving us the y1, y2, and the x. Yes, yeah, correct.
This one.
Yes.
Okay, I thought we did it. Okay. Let me share the whiteboard and then we will use the whiteboard.
Okay.
Okay, because there isn't so much space here.
Thank you.
All right. And please, can you see the whiteboard? Okay. At the moment, you can't even answer. So, because I have disabled you. All right. But if you can see the whiteboard, please say yes in the chat so that I know I'm sharing it. If you can't, to kindly say no for me. Okay, you can see it. That's fine. Thank you for answering. Okay. All right. So I was talking about using a system like y is equal to 2x. Okay. We want to determine whether this system is linear. So if the system is linear, so if this system is linear, then it should satisfy additivity and homogeneity, right? So the system should satisfy these two. Now, additivity means that when we have y, so let me write here. So for additivity, right, when we have y is equal to 2x, okay, y1, sorry, is equal to 2x1, and then y2 is equal to 2x2, right? Then y total, which is equal to y1 plus y2, should also be equal to 2 into brackets s1 plus x2. If we find y total for y1 plus y2, and then we find y total for 2x1 x plus x2, and the answers are the same, then it means that it has additivity. Okay, so let's go through that and see. So still working on the additivity. Please let me put a line here, then we continue. Okay, so now y1. So let's say x1 is 2 and x2 is 4. Okay, then y1 is equal to 2 times 2 and y2 is equal to 2 times 4. So here we have 4 and for y2 we have 8. Okay. Now, this means that y total is equal to y1 plus y2, which is 4 plus 8, and that gives us 12, right? Now, let's look at y total again. For it to be linear, we should be able to find that y total is equal to 2 times x1, which is 2, plus x2, which is 4, right? And that is 2 times 6, and 2 times 6 gives us 12. So this means that this system y1 plus y2 is equal to 2 into brackets x1 plus x2. Then it means that the system is additive. Okay, so it has additivity, so which means that the system has already satisfied the first requirement. Now we need to check its homogeneity, right? So for the system to be homogenic, this system should be scalable. So this means that when we scale the inputs, when the input is scaled, we should have a corresponding output for when the input is scaled. Okay, so when we say scaled, it means that we are multiplying the input by a certain scalar value, right? So scaled is to multiply the input by a scalar and then multiply the output by the same scalar and see if we get the same output, right, when they are scaled. So now let's choose a scalar. We are calling it alpha, and then we are choosing alpha to be, let's say, -5. So which means that now our input x, let's say that x is actually equal to 2. Okay, when not scaled. So then it means that y, okay, we already have x1, so let's use y1. y1 is equal to 2x, which will give us what? 4. Now we are going to multiply x1 by the scalar value, okay, which will give us what? -10, right? And then we want to see if multiplying x1 by the scalar value is also going to give us the same y1 times that same scalar value. Okay, so we want to see if y1 times alpha is equal to 2 times alpha x. That's what we want to see. And alpha x is minus 10. Okay, so alpha is what? Minus 5. So we want to see if minus 5 times y1 will give us 2 times alpha x, which is minus 10. Okay, so that's what we want to see. Now minus 5 times y1 is equal to what? Minus 5 times 4, which is minus 20. And then 2 times alpha x, which is here, please, okay, is equal to 2 times minus 5 times x is what? 2. We've already done the alpha x, which is 2 times minus 10, which is also equal to minus 20. So we see that alpha times y1 is actually equal to 2 times alpha x. So when we scaled the input, we got a corresponding scale in the output, and therefore this system, which is y is equal to 2x, this system is homogenic. It has homogeneity, right? And because it has been able to fulfill both conditions, this system is linear. Y is equal to 2x is linear. Okay, now let's look at and the other system, which is x squared system, right? Let me take another whiteboard. So we want to see if y is equal to x squared is linear, right? If y is equal to x squared is linear, it has to satisfy the two conditions, additivity and homogeneity. So to do that, we'll just take arbitrary numbers as x, and then we will check. So now to do that, let's check for additivity first. Okay, so we are checking for additivity first. So it means that we have arbitrary values for x1. Let's say x1 is 2, x2 is 4, like we had at the beginning. Now this means that for additivity, y1 plus y2 should be equal to, when we add the x's, x1 plus x2 all squared, right? It should be equal to that. y1 plus y2 should be equal to x1 plus x2 squared, because the x is what is here. And it is, we find the sum of the x's, square that, and see if it will give us the same as the output individually summed, right? So now y1 is equal to x1 squared, y2 is equal to x2 squared. Okay, so for the first one, y1 is what? 2 squared, which is equal to 4. y2 is 4 squared, and that is equal to 16. Okay, now we want to check to see if y1 plus y2, when we have these outputs, will give us the same as x1 plus x2 all squared. So y1 plus y2, it will be equal to 4 plus 16, which will give us 20. Now let's check for, okay, so hey, where is my point? Okay, it's here. I can't see it. So now let's see if y total, which is equal to x1 plus x2 squared, will be equal to the y total. So this is also y total. Okay, we want to see if this y total will be equal to this y total. So x1 is 2 and x2 is 4, right? When we square that, we have this y total being equal to 6 squared, and that gives us 36. So we see that the y totals are not the same. So y1 plus y2 is not equal to x1 plus x2 squared, meaning that y is equal to x squared is not additive. Okay, you cannot add the inputs, put it in the system, and then you get an addition, a raw addition of the outputs. Okay, so this is not additive, right? Now to check if it is homogenic, I don't know why, but I cannot see. Now I can see it. Now I can see my pointer. So now let's check if it is homogenic. So we are checking for homogeneity. So there we are going to scale the input and see if it corresponds to exact scaling of the output. Okay, so we will check the corresponding output. So this means that the input is, we are looking, let's say just y1. y1 is equal to x1 squared. Now, if x1 is scaled, which means that we are going to multiply x1 with alpha. So we have alpha x1. Okay, then that is going to be the input now. We will scale alpha x1 and make that the input. So this becomes the new input. Now, if we input alpha x1, so alpha x1 squared, we want to see if y is equal to alpha x1 squared will be equal to, will give us a corresponding value of alpha y when we multiply the output, which is y, by alpha, right? Remember now, all we are doing is just multiplying by alpha. We multiply the inputs by alpha, then we multiply its original output, which is y1, by alpha, and see if we are going to get the same value. So this one is y1 scaled, and then we want to see if we will get it as alpha times y1, right? So let's choose -5 once again as our scalar quantity. So now it means that the second input is going to be -5 times x1. Okay, that will be our second input. So first, y1 is equal to x1 squared, and x1 is 2. So y1 is equal to 2 squared, which is equal to 4. Okay, now the second input is what? Alpha times x1, and alpha is -5. So alpha times x1 is going to be -5 times 2, which is -10. Okay, now when we put -10 into y, we are going to get -10 squared, and that is what? 100. Okay, and now let's see, alpha times y1. Alpha is -5. And when we multiply that -5 with y1, this is y1, right? So times 4, we are getting -20. So we see that over here to the y1, when we scale it, is not equal to alpha y1, right? So this means that the system y is equal to x squared does not have homogeneity. It doesn't even have additivity. So it is so not linear. It is a non-linear system. Okay, so I hope that it's what I have said right now is understandable. Some people have, please madam, I can't see what you are writing on the whiteboard. Hey, really? But the whiteboard is also sharing. It's still sharing, but some people can't see. Madam, please, I can't see. Different people have written that. Will there be a system that has a continuous time signal at the input and gives a discrete time signal at the output? Yes, that is a system that is supposed to convert it's supposed to convert maybe analog signals to discrete time signals, but rather I should say it's supposed to convert continuous time signals to discrete time signals. Okay, such a system is going to have a certain output, which is discrete time, but its actual input is continuous time. Oh, sorry to those who can't see. Somebody says, please, madam, it's very clear now. Okay, all right. Thank you for giving me feedback that you understand what I have said. So those who can't see, very sorry about that, but we are recording and I'm recording the screen. Okay, so hopefully the screen is recorded, and then I will also share the whiteboard as a PDF so that maybe you can look at it and then follow later. Very sorry that you can't see. Okay, so we will leave the whiteboard and then continue to the slides. Madam, please, is a system that has multiple inputs but single outputs, or is there a system that has multiple inputs? Yes. A multiplexer is an example of such a system. Okay. Then somebody is asking, please, madam, is the -5 a constant value? Yes, it is. We are calling it a scalar value. It is just a magnitude, an arbitrary magnitude. We are multiplying by the inputs and then the output to see how the system is going to perform. Okay, so it is just a test, let's say a test value. So it is a constant value we are using. We chose it, all right? We just chose the -5 as our scalar quantity that we are going to multiply with the inputs of the system and then the output of the system to see if there is a corresponding change in the output when this input is scaled to that level. Okay, that helps us to see if the system is linear. And by doing that, we're able to see that 2x is linear, but a system that is defined as s squared is not linear. Okay, so let's share the lecture notes once again and then continue from there. Okay. So elements of a communication system. So the communication system is also a system. It is made up of so many subsystems, right? But the major requirements of that communication system is that we should be able to reproduce the input signal at the final user's output. So when we put in a certain signal to the communication system, we want to be able to receive that same signal at the output, which is when the user receives it, right? That user is supposed to be able to see exactly what we wanted to send to the user. So it's a system that conveys information from its source to the destination, and it's supposed to be some distance away from the source for it to qualify to be a communication system. Please, somebody has another question. He says that in this case, are we going to give a value in the midsem? Oh, okay. You are thinking about the midsem. If you are supposed to prove whether a system is linear, you have to choose your own values. You have to choose your own values to determine if the system is linear. So if your system passes the two conditions, which is additivity and homogeneity, based on your own choice of scalar quantities, right, then it means the system is linear. I mean, based on your choices of scalar quantities, if you prove that the system is linear, I mean, and it is right, of course, then it is linear. All right, so I just chose the -5. You can choose any number. You can choose -10. You can choose 2. You can choose 0.5. You can choose 100, a million. You can choose any value at all. Okay. So, and then after here, when we are done, we will discuss how the midsem will be. Okay, so we decide how we should make our midsem. Looking at the scalar values used, they all happen to be in the negatives. Please, is there a reason for that? Yes, I intentionally chose the negatives because the negatives will be easier to prove that, especially with the x squared, that when we use the negative as the input, we are actually getting a positive at the output, and we are getting a negative when we multiply the negative with the y1. When we multiplied -5 with y1, you see we were getting -20, which is a negative. However, when we multiplied -5 with the input, which is 2, right, and then we squared it, we got +100. So that clearly shows, even if our outputs were +1 and then the y will give us -1, right, that clearly shows that the system is not homogenic. I mean, it's easy to prove homogeneity and additivity with the negative values. That's why I intentionally chose them. But you can choose positive values. You will still be able to prove that x squared is not linear. Okay, you can choose any value at all. And like I was saying, when we are done, we will discuss the mode of our midsem exams. Right. Okay. So back to the communication system. The communication system is a function of distance. It has to happen over a certain distance for us to be able to determine how effective the communication system is. And the main elements of the communication system, the essential parts that determine how the system is working over a certain distance, include the transmitter, the channel, and then the receiver. So for any communication system, we should have a system that will be transmitting, okay, the signal that we have. Then it should pass through a certain channel. The channel can be wireless or it can be wired, which means that it is passed through cables. That is having a wire, maybe optical fiber cables, or maybe coaxial cables, or whatever cables, right? But we are using a cable to transmit. the signal from one end to another. And then it should have a receiver, a point when the signal is received, and then that signal is put in a way that the user will be able to relate with. So the transmitter is the end that converts the signal. So it converts the input signal to a mode that can be sent over the channel. For example, if I connect my laptop to the projector, right? The projector, the cable that is connected to the projector cannot transmit the picture as we see the picture shown on the board from the projector. It cannot. It only transmits electrical signals. So the transmitter should be able to pick the picture information and convert it to electrical signals. Then these electrical signals are then put into the cable that is connected to my laptop from the projector, right? Then when it gets to the projector is the receiver. The projector now receives the signal, and then it now converts the signal back to picture information. And that picture information is displayed on the screen, on the board for us to see. All right. And so the transmitter is very important. The channel that is going to carry the information from the transmitter to the receiver is important. The receiver is also very important. Without any of these, we do not have our communication system. And that's why they are the essential parts of any communication system. Okay, so we want to talk about the information, that is the message that is sent, where that message comes from. The message signal that is sent comes from the very ordinary source, which is most of the time the natural form. For example, if we are transmitting voice signals, right? That voice should come from maybe a human being, or maybe it's a dog that is barking. It's still a sound, okay? The voice of the dog is the one that is barking. So the sound signal should come from a certain source, right? That person speaking is causing changes in the pressure of the air around, and that is creating vibrations that the microphone is able to pick. So the microphone is sensitive to these variations in pressure within the air, and then it's able to convert these variations into electrical signal, right? So the microphone there is our first point where the signal is converted to electrical signal. Now, this electrical signal can then be given to a certain transmitter, right? For the transmitter to carry the signal and then also convert it to a mode that the channel will be able to relate with, right? And so the source, primarily most of the time, the source comes from the natural environment. But there are some sources that are generated by computers, right? So those sources that are generated by computers are usually digital sources. However, the sources that come from the natural environment, they are analog signals. And when we go to pulse code modulations, we'll be able to differentiate between analog and digital signals more easily. Okay, so that is where the message is from. Now, the goal of the communication system is supposed to be able to reproduce the message signal that is given the transmitter at the receiver's end without any loss in the information, and we know that that is quite impossible. Certainly there will be some losses in the channel. However, the losses are supposed to be managed in such a way that it does not affect the integrity of the signal that is transmitted. Then we know we have a very good communication system. If the results or the response, what the receiver receives, is so bad, then it means that the communication system is not working efficiently. There are too many losses within the communication system. Okay, so I was talking about the information that is received from the source being converted to electrical signals primarily, and these are done by what we call input transducers. Sometimes you call them sensors. So the microphone is an example of an input transducer. The input transducer, it's able to convert energy from one form to another, right? And output transducers also convert electrical energy into maybe chemical form, into other forms that the human being is able to relate with. Okay, so input the input transducers convert from one form to the electrical form, and the output transducers converts from electrical form to the original, something similar to the original form. Okay, so we have said that the transducer is a device that converts energy from one form to another, right? So like we said, the input transducers, they convert energy maybe in the form of sound, light, heat, etc. to their electrical form, and then the output will convert from electrical form to other forms, maybe to the sound, to light, to heat, etc. Okay, so these are examples of input transducers, and these are examples of output transducers. Okay, so when we put in the inputs, that when we try to put in all of the transducers within the communication system, then instead of just having the source of information going directly to the transmitter, the source of information will first go to a certain input transducer. Oh, it's not writing it. Input transducer. Okay, so this is the input transducer. And then before it goes to the user of the information, there is supposed to be an output transducer there. So this output transducer receives it, and then it converts it to a form that is quite close to the original form, right, for the user of that information. Okay, and so that is what we have put here, right? Now, if at any point maybe you receive such a question that requires you to include the inputs and the output transducers within the communication system, you are expected to complete this communication system by showing the elements, not just writing communication system, but including the three elements of the communication system, and then allowing the rest of the data or the rest of the figure here to also be represented. So that everything here with the three elements of the communication system also represented within this portion. Okay, so the transmitter side is where the input signal is processed to be suitable enough for the transmission channel. Okay, so the channel, like we said, can be cables, and it can also be, let's say, infrared. Maybe it is not infrared, but it is Bluetooth. Though the both channels are using the space between the transmitter and the receiver, which is the air or the environment, it is still using a certain specific frequency for transmission. Okay, infrared frequency is different from the frequency of Bluetooth. Maybe it's Wi-Fi, whatever it is. The message is carried on that, and so the transmitter has to process the input signal so that the signal can be carried via that channel. Okay, and sometimes the transmitter is also connected to the antenna. So the transmitting antenna is also collectively known with the transmitter as the transmitter, and the receiving antenna may also be known together with the receiver as the receiver. Okay, so though they are the antennas, especially for wireless transmissions, you always need an antenna to transmit and an antenna also to receive. The antenna works with the transmitter at the transmission end, and the receiving antenna also works with the receiver at the receiving end, and combined we usually refer to both of them as the transmitter, and at the other side to the transmitter and the receiving device as the receiver. Okay, so within the transmitter, some processes that occur include modulation and then encoding of the signal, right? We will understand modulation and encoding later on, but we should understand that this occurs in the transmitter. And the receiver, within the receiver, operations that usually occur are amplification, because the signals will certainly be attenuated before they get to the receiver. So the receiver has to pick it up and then amplify it. Sometimes the receiver has to filter noise out. The receiver also has to decode if the signal was encoded, and then if the signal was modulated, the receiver has to demodulate it. Right, so all of these occur within the receiver before that signal is then given to the transducer. The television, within the television, right, we have the television working both as a receiver and also as a transducer. So the transducer system within the television is what converts it to pictures and video for us to see, okay, as well as the sound portion for us to hear. So what we can actually communicate with is the video or the picture on the screen, as well as the sound that is coming out. We do not really understand, or we cannot really understand, the electrical signals within the television. If we were only to see those signals, we will not be able to convert it by our own minds or our brains or by our eyes as video, right? But the television system is able to convert these signals as video output for us to see, and then also as audio for us to hear, right? So it is acting there as a transducer, an output transducer, right? But it is also the receiver, which does the demodulation, it does decoding, it does filtering, it does amplification, and then it also shows us the picture and also gives us the sound. Now, in transmission, we have three major modes for the communication system. We have the simplex mode, we have the half duplex, and then the full duplex. Right, the full duplex is here. Now, the simplex is the name, what do you call it? The name supposes or suggests. It is the simplest mode. Okay, so now the word is simplex, right? But I'm playing over on the word to say it is the simplest mode of communication. It only occurs in one direction. So we say it is unidirectional, just one direction, right? From the transmitter to the receiver, that's all. The receiver does not retransmit, or using the same mode of transmission from the transmitter, the receiver does not send feedback or anything via that same mode. Okay, and so we say it is unidirectional. An example is television transmission, right? When you watch television, let's say you are watching GTV Sports or something, whatever you are watching is coming from them to you. You don't send a feedback through your television. Maybe you take your TV and then you send a feedback that we cannot really receive the signal well. Can you do something about it? You don't do that via your television. If you want to give them feedback, you have to call, and that is a different mode of communication. Okay, you have to call them with your phone and tell them that, hey, what you are bringing us is not really what we are asking for, or something like that, right? So for the simplex, you do not send, the receiver just receives and doesn't send any feedback to the sender, right? And half duplex is an upgrade over the simplex. Okay, the simplex, because it only transmits, we only need one communication channel. We don't need two, because the receiver or the second, let's call this A and then B. For the simplex, when B receives from A, B is not able to send feedback or say anything back to A, right? However, for the half duplex, they still use only one channel to communicate. Only one channel, and a signal, only the channel can occupy just one signal stream at a time, right? So when one channel is given, it means that if A needs to transmit anything to B, A alone is supposed to use the entire channel. So A uses the whole channel, sends information to B, right? And so B should be ready to listen, because B cannot transmit at the same time that A is transmitting. That's for the half duplex. However, A can also receive from B. Okay, so at a point, B is a receiver, and at another point, B is a transmitter. It sends information to A, and A now keeps quiet and also receives from B without using the channel. So which means that at every point in time, the half duplex channel is dedicated to one sender. The sender may be A or it may be B, but whilst it is dedicated to A, it is not open for B to send. And when it is dedicated to B, it is not open for A to send. An example of that is the walkie-talkie, right? That's a clear example of the half duplex. And you know that with the walkie-talkie, always the receiver has to wait for the transmitter to, the one transmitting or the sender, to finish sending his information before that person can also use the channel. And they have designed the walkie-talkie in such a way that if I want to use the channel, I need to press a certain button. then the channel is available to me, and everyone else has to listen to what I have to say. And then when I am done, if B has a response, then B can also press the button and make use of the channel, right? So it is just one channel and we only use it in turns, right? But the best of all, the greatest advancement over both of them is the full duplex. For the full duplex, there are two channels. Right, like I said, a channel is dedicated, okay? So one channel is dedicated for A to always be sending to B. And B also has a dedicated channel where it sends always to A, right? So B's channel goes continuously from B to A, and A's channel goes continuously from A to B. So which means that when A is sending a message to B, B can also be sending a message to A at the same time. And this is possible because they are not using the same channel. Because when a channel is given to A is having that channel for A's communication, for it sending information to B continuously. Okay, that's why you say dedicated. And then B also has a channel that it uses to send information to A continuously, right? So over here, communication in the full duplex occurs simultaneously, right? Communication is occurring simultaneously in a two-way fashion because there are two dedicated channels, one for A to send to B and one for B to send to A. However, the half duplex one, because there is only one channel, they have to wait their turns. So A will send to B, B has to wait its turn. When A is free, when A is done, then it means that the channel is free. B can also send to A. But in full duplex, two channels are available, and so there is no waiting your turn. You just send if you are ready to send, and then you receive whenever the sender also sends to you. So this is it for lecture notes 2. Now I am open for any questions, please. You can unmute yourselves if you have a question, and then you can ask. When you are done, then we will discuss the mode of our midterm exams. Please, if you are finding it difficult to unmute yourself, let me know. But I have checked that it should allow all participants to unmute themselves. If you have a question, kindly unmute yourself and ask. All right, since no question is coming, let's discuss the form our midterm is going to take. Okay, so let me stop it so that we can save some data. Okay, so how do we want our midterm? Do we want MCQs? Do we want maybe 2 or 3 questions to answer? Any of these is viable. If it's MCQs, then we will probably have 30 or 40 MCQs. And that's all we'll be doing, but it will be given for us for an hour. If we will solve questions, then that will also be done. But according to the new rules, we have to have a midterm, right? Otherwise, last year, we just had an assignment, the midterm as a take-home assignment, but it seems that the new rules are that we should have a mid-semester exam. The other option would have been to go and do it online at the V class, but I know people are going to reject that idea, so let's discuss it.
Madam, we want MCQ.
MCQs. Okay.
Yeah.
All right. Okay. Please, do we all agree with the MCQ's idea? Okay. From Samuel, we can't say MCQ.
One MCQ.
Okay.
So, madam, please, I have a question.
Please, let's go.
So please, if it's MCQs, are we going to write it on campus or it's going to be online or
you
in
write
which
on
mode?
campus. The
okay.
two can be MCQs. Right, but most of the time, top-up students don't like the online one.
Oh, okay.
Yeah, I always have a struggle, getting top-up students to go and do quizzes online. So then you do it in class, but it will be MCQs.
Okay.
Hey, somebody says what? I'm afraid of your MCQ. Oh, I don't know. Please, madam, let's write the theory questions. I'm afraid of your MCQs. Oh, okay. Let's not be scared of the MCQs.
Madam, so we prefer the MCQs.
Okay. So since there are a few who don't, kindly make a decision on your class page, okay? And then you send me the final verdict, right?
Okay.
Yes, and then we will just do it in such a way that everyone is comfortable. Right? So don't be too scared. If you are doing regular, yes, then maybe you can be scared, but for top up, well, you are workers mostly, so sometimes we try not to overload you, right? So yeah, if it's MCQs, I think it will still be comfortable. Just read what we have done, and then also we have lecture 1 and 2, so which means that our MCQs will cover the two. Okay, so whatever we do next week Monday when we meet will not be seen in the midterm exams, right? But the good thing about the midterm when we actually write it also is that for especially the weekend, the top up, it's sometimes you will find some of them reflected in the main exam. So at least it gives you some backing and some idea of how the main exam is, right? Yes, and so let's also discuss the main exam, right? Would you also want MCQs completing the main exam because you have to submit? Or maybe we can do MCQs about 45 and then we have maybe answer one question in the theory side. I think
Yes, madam. We want
Yes, madam.
40.
That one is better. Yeah.
Yeah, that one is better. And then answer one question.
okay, out of
Yes.
maybe
You will
2 or 3. Okay, all right. So,
Yes. So one question and the rest will be MCQs. That's
all
all.
right. So that's how we will do it.
Okay, thank you.
Okay. Then have a good night. We meet again
Okay. Thank you, madam.
next week. Thank you too.
Thank you so much, madam.
Thank
Good
you. The
night.
same to
Thank
you.
you, madam. Have a
God
wonderful
bless you.
evening.
You,
God bless.
thank you.
Madam, thank
Bye.
you very much.
You, thank you too for joining the class. All right.
Thank
Good
Thank you
night,
very
everyone.
much.
Bye bye.
You,
Good
bye.
night.
Bye bye.
Bye.